Everything okay here?
I know the answer for that one. I just don't.
Sound is fine. Okay.
That one too.
Happy Tuesday. Welcome back to Probability Vault. Okay, for attendance today, there is a quiz. We can go. Actually, do you remember I gave you one assignment to do? You can enter the answers there, this assignment. Tracking two targets. If you go to Canvas, can you check it out? If you go to Canvas and Module 2, there is something like homework there. Quiz there that mentioned attendance. If you click on that, you can open. I asked same question there. I want you to answer that. And at the same time, that's also kind of checking your attendance as well. But I'm going to give you the answer here, but I want you to try first. But don't submit it. So in this example, last class we explained a little bit, is about axioms. However, this is not about axioms. This is about two parts. First of all, mentioning we have two targets, A and B, and we are using sonar. Sonar normally is a type of sensor that use underwater most of the time because sound passing very good underwater. So most of the time, if you want to detect something underwater, sonar is a good idea. But sonar has some, limitation as well. Anyway, here we use a sonar to detect targets, and we have two targets, A and B. So imagine there is AUV. AUV is a kind of autonomous robot underwater. Autonomous underwater vehicle, AUV. So AUV normally use, so imagine this is AUV, and it's using sonar. Sonar is making sound underwater and check the reflection and can detect objects. Imagine there is two objects that are A and B, and when these waves hit them, the reflection can be listened. But we mentioned something here that a radar is tracking two moving targets using sonar sensor. At each time step, the sonar returns one measurement. This is important. And each step, the sonar returns just one measurement. It can't get two measurements at the same time. It means these two events, A and B, are actually mutual exclusive. They can't happen at the same time. That's the main point. If they are mutually exclusive, P of A and B is 0. So P. Probability of A and B is 0. So what else we can say? OK. And also P of A plus P of B, and P of A or B is P of A plus B. We had that also in last axioms for probability axioms. So we have this idea. So what we want to find, first of all, ask us what is sample space. So because we have also false alarm, because sometimes maybe there is a fish over there, and this fish can consider as a target. Imagine there is a fish here, And this is also act the same way. So this is false alarm. False alarm or outliers can be happened a lot in tracking, in detection, in perception. So in this case, we consider that also as one of the situations that happened in this scenario. So sample space is considering that as well. So what is sample space? If you look at in your actually quiz, it has multiple options. One of them is actually target A, target B, and false alarm. That's, of course, that's the correct one. So target A, target B, and false alarm. This is sample space. OK. Another question is that what is the probability that the measurement is associated with the real target? So it means remove false alarm. So it means P of A or B. So as we already explained that these two events are mutually exclusive, so it means if they want to have both, we need to add them together. And we have them. P of A is 0.6, and P of B is 0.3. So the overall 0.9 is a P of A or B. OK? But we also ask what is the probability that it is a false alarm, but that's already given. But the reason that I ask this, because probability of false alarm is kind of complement of this one. So instead of using this, you can just say, OK, probability of false alarm, if we call it P of FA, is equal to 1 minus 0.9. That is 0.1. Later on in this lecture, we're going to see this is considered complement probability. We call that complement probability because they complement that. And it's coming from second axiom, that normalization. So the sum of all the events need to get 1 in overall. OK, so that was example. Please finish that quiz.
Access code for it.
Yes. You can open it?
An access code.
Oh, access code, yes. Access code is, actually, I don't remember. Oh, yeah, 0104. Let me write it here. 0104. That's access code. Can you open it now? Good? OK. So, yeah. Good? You're done? Perfect. So what we're going to do today, so that was from last class. Today we're going to talk more about conditional probability, like continuing last class. Conditional probability is important. Also, we're going to talk about chain rule or multiplication rule. Um, there is a quiz in, you did it? Not yet. Yeah. The passcode is 0104. Yeah, 0104. Okay, so we're going to talk about conditional probability, chain rule, or multiplication rule. That chain rule is kind of coming from conditional probability formula. We're going to see that soon. Also, we're going to talk about independent events. When two events are independent, it means if you know one of them doesn't affect the other one. They're not related. And we're going to talk also about complement events, the one that we already saw, like probability of A. Do you have questions? You're good? OK. And also, we're going to talk something else if we get chance that is called total theorem. That is very amazing theory regarding to probability, of course. Let's get started. We already talked about this example. So the answers for this example, for you that, sorry, the answers are here. I don't want you to make mistake. OK. Next slide. Independent events. OK? Sometimes events are independent. So it means if you know, for example, information about one, it's not affect the other one. So you can say, OK, probability of A and B, if they are independent, is probability of A multiplied probability of B. Or also we can say probability of A given B if A and B are independent is equal to, so because if we know B doesn't affect A, so is equal to P of A. These two properties are very important for independent events. So especially the second, however, you can use that they are just coming from each other, and we can prove them. So if knowing one event doesn't change the probability of other, this is called independent. But don't make mistake independency with mutually exclusive. Mutually exclusive means they are not happening at the same time. They don't relate it. They are not connected to this. It's not related to this. We can see that. There is one example. We can see that. OK, so the first property, as I mentioned, as I wrote here, is this. Because knowing B not affecting A, so P of A given B is P of A. OK? And P of A and B is also P of A plus P of B. Notice that probability of A and B, if there is mutually exclusive, is 0 for A and B if they are mutually exclusive. P of A and B is 0. This is something that you need to consider. But if it's independent, is multiplication of probability of A and P, probability of B. OK, so this is something to know. So the takes away part is very simple part. It's just multiplication directly. OK, so it makes sense. Yes?
Like a chart that would show an example of two independent.
Sure. Yeah. Like a Venn diagram?
Yeah.
Sometimes in Venn diagram, you can show this dependent, but I can show you soon. Yes, we have some. Yes?
Isn't an example of independent events when you have like a set amount of like, I remember like marbles in a bag, you take one out
Oh,
and change them.
independent. For example, we can see them. Just wait a second. We're just going to have example right now. This is one of the examples that we can see. I'm going to answer this question, but wait a little bit to go a couple of slides further. You're going to get answers. One of independent example actually is this example. You know, OK, before that, I'm just going to recap about conditional probability formula that we had last class. So in conditional probability, we know probability of A given B is kind of removing B outside. You know, because B is kind of uncertainty too. That's why we divide it by B means kind of we are removing this uncertainty. Do you understand what I'm saying? I'm saying probability of A given B, because we already know B. We need to take that out of our uncertainty. So how we do that? We divide it by P of B. This division makes probability higher. OK, that's some intuition about this formula. But we have example here. We had that last class. Remember? We had that last class. We tested that for that card exam questions. We said there's a king and colors, and we considered that. But here we have another example. We have, as you can see in this picture, there is a car including some sensors. This car has two sensors, camera and LiDAR. Most of autonomous vehicles have these two sensors because they complement each other. They have LiDAR. LiDAR give you 3D points. And camera give you, 2D dimensional, but lots of colors there, lots of information in camera. However, you can use multiple camera to do same way that LiDAR working, get depth out. Multiple camera, like some vehicles, like Tesla, are not using LiDAR. They just use many cameras. And they think, why we use LiDAR? LiDAR is expensive too, and need also fusion. LiDAR give you different information than camera. You need to fuse them together. It's very complicated. Fusion is very complicated. We can see that later in other courses. But anyway, this car that including these sensors can detect other obstacles around, like pedestrian here, or other cars here. This car also called, what's it called? It's called ego vehicle or ego vehicle. Ego means I in Latin. So when somewhere you say, OK, ego vehicle or ego object, it means the vehicle that include these sensors to actually get perception. So this is called ego car. So in this picture, you can see this information coming from LiDAR and some other information coming from camera. This is just extra information about this example. But in general, we have these settings. And we know probability of detecting using camera is 0.8. And probability of detecting obstacles or targets using LiDAR is more, because it's more precise. And when you are detecting based off camera. In camera, there is lots of false alarms. Like, for example, if your car driving in the street and it said, see a picture of pedestrian in a wall, it can detect it as a real pedestrian, but that's just a picture. You know what I'm saying? That's kind of false alarm. But LiDAR can detect that because it detects three-dimensional points. So that's different between these two. That's why it's higher. OK, what we ask? First, we assume these sensors are independent. Because they are independent, they don't really show. They have different sensors. This is an example of independent case. So detecting by camera, not effect to detecting by LiDAR. They are independent. They don't have any relationship together. You know, if one of them not work, the other one is still working. That means independency. Okay, that was the example that you asked about independency. Okay, what they ask, what is the probability that the camera detects the obstacle, given that the LiDAR also detected obstacles? So we want to find probability of probability of C, sorry, given LiDAR. We want to find this. So, but we know that they are independent. So P of A and B, P of B, because they are independent, it can be P of A multiplied P of B. And P of B, they cancel out, and it's going to be P of A. Oh, sorry, I should put C and, OK, I'm sorry. A and B. Or you can even directly write that. Like this is equal to P of C, so 0.8. OK. In terms of Venn diagram, we can't show exactly this division, but I'm going to show some part of that, the question that you asked about Venn diagram. So in Venn diagram, imagine this Venn diagram. We have A and B. OK? So P of A and B is this one. Actually, it's not P, it's A and B. This is, yeah, A and B. And P of B, this is B. So when divide P of A and B over P of B, so anyway, we can show that like that, because here we have probability. But in some cases, we can prove using a Venn diagram. But in here is not a way to using that to prove it. Yes. But it's going to help us a lot to understand what's going on. Yes?
Interpret the left side of the equation?
Yes, yes. That's a very good question. Yes. Again, I can explain what's happening here. So P and B is that part. But P of B is uncertainty about B. We want to take that uncertainty out because we know about B. So when we divide the value of P and B over P of B, we make that smaller. Probability becomes smaller. I mean, probability becomes higher. Probability becomes higher. I mean, it has more probability. So yes, like what's happening here. what's happening here, however, because they are independent, so probability of A and B is going to cancel out by probability of L. Okay, let have more example. We're going to have more example in this case. Okay, but just for intuition to what's happening in that formula, we are taking uncertainty of B out with division. Did you get your?
Not exactly, because
Not exactly.
down that left side of the equation.
Oh, you are talking about that? I was thinking you were asking.
No, the bottom part.
Oh, you are asking. Oh, you are saying why this is happened?
No, not why, but like how do you interpret?
Yes. So this was P of C and L, P of L, and P of C and L, because they are independent, is P of C, P of L divided by P of L is P of C.
Oh, okay, got it.
Yes? Here you can see more clear.
How do you say the left side? Like just like the P, C of L.
Given. That line means given.
Oh, how we can say that? That means given. Yes.
Gotcha.
Yes, that's given. It means we know already L. So you can see that given that the LiDAR. We're going to have more examples. If it's not clear, don't worry. We're going to see that a lot. Yeah, but let make this formula a little bit, look at that formula a little bit different. P of A given B was P of A and B over P of B. Because we know B, we want to take B out. And if we multiply two sides by P of B, it's going to be P A and B is equal to P A given B, P of B. This is called multiplication rule. Very simple. So it means you can find probability of multiple events happening at the same time. That's the point. Probability of multiple events at the same time is the hardest things to compute because they are related sometimes. So that's going to be a problem. Yes?
Is this only for independent?
It's only for independence? No, it's not for only independent parents. No, it's for all of them. Okay, because for independent, this is going to be, okay, imagine it's independent. Let's see what's happening. P of A and B is going to be P of A, P of B for independent. Why? Because this is P of A. Remember, in independent? Okay, I'm just going to come clean this up. Okay, let I clean up all the, because I'm going to have it here. Okay, so that's called multiplication rule. But what about 3 events, A, B, C? What about 4 events? Can we expand it for more events? Yes, we can. P of A and B and C, we can do the same thing. Because multiplication rule, also called chain rule, you have many events happening at the same time. How we can compute them, how we can find them. P of A given B, because we can consider this as a D event. So we can say P of A and D is P of A given D. D is B and C. P of D and we can write this is same. This we can write it again. P of B given C P of C. Let's write it. P of A and C. It's called chain rule or multiplication rule. It has so many applications. We can see that in AI. Chain rule is the base of AI. And later on, maybe in this class, end of semester, I talk about graphical method. And this is the basic of graphical models. You can consider parents' relationship and child relationship in this chain rule. We can see that later. Don't worry. Let's go for 4. You do it for 4. P of A given B given C given, and D and C. What is this? Can you compute that? I'm going to come check. So just you can consider this part as another event like E and go step by step. So let's change the color. So this is going to be P of A given E, that E is B and C and D. And the rest is P of B and C and D. P of B and C and D. And write this again. This is same. P of B given C and D. P of C and D. This is finished. And P of C and D is P of C given D, P of B. So if you write them all together, it's going to be P of A, B and C and D, P of B, C and D, multiply P of C and D, multiply P of D. As you can see, we break that down with multiplication. So, and this is very important in actually perception. Because, for example, you say, OK, what is the probability of a robot be here given lots of other information? You can break that down with some multiplication things. And multiplications can change to addition. We can see that later. Anybody can tell me how multiplication can change to addition? It's complicated, but in probability, these things happen. OK, any questions about this before I mention that part? Any question about this? So the point is probability of multiple things at the same time. We need to break that down because it's so complex. Probability of multiple things that is happening at the same time. It's so complex, we need to break that down to smaller probabilities and multiply them together. But still, multiplication is not linear. Linearization, make things linear, is very important for us. When we make things linear, we can solve them in linear time. We can solve them easier. What do you mean by solve them? Solve them means finding some of these variables. Later, we can see they are like variables. We need to find them. We need to find them. OK, let I clean this to have some space here to explain. Like, for example, you can say probability of X given Z. This is a robot, that the position of this robot is X, like 5 and 10 in the grid. And this robot has some sensors. like for example, is a LiDAR in top, it's turning and give you information. That's Z coming from those information or measurements. And solving this problem means finding X. What is X? X is the position. We want to find it based off the measurements that we are reading. This is all probability. And you can find that. We can see how we can compute that. I just wanted to say what we want to find. And if we break that down to multiple things, like for example, P of Z, given Z1 and Z2 and Z3, maybe you have multiple sensors. So if we break that down to something like P of, this is X. P of X, okay, I'm not going to write that. I change that to multiplication. How we can change this multiplication? Because we want to find X. And this is the probability of X. So if we have probability of something and we want that X, just need to maximize that probability. So we can say X is actually max of, or argmax, of X given Z1, Z2, Zn. Argmax X. This is how we can find X. Okay. And argmax and argmean, you can change it to argmean too. We just need to make it negative. Do you know some optimization? Have you learned any optimization in your? You had some optimization. So that's what I'm talking about. This is kind of optimization. We change that to optimization problem, and you can see how. Because it's probability, we can make argmax, like find the X that maximize that probability. And this is P. And then we can find X. There is so many ways. We're going to see that later. But how we can change multiplication to addition, it depends what is this probability. If this probability is an exponential family, like exponential of X, for example, or a function of X, in this case, log going to solve the problem. OK. I'm not going to go more because it's too much details. We can see that maybe later. But log can help. Log always change multiplication to addition, remember? And log is not change the trend. If you want to find maximize of something, if you get log, still that is similar. Log is not changing the trend. OK? So that's very important. OK, so we're going to see that later. So that's multiplication rule. This is for 3, and for 4 I computed. Let's do one example. OK, there is another example, just again, camera and LiDAR. We have two sensors, camera and LiDAR. We want the probability that both sensors detect an object. OK? Both detect object. Let's see which example was that. OK, 90 and yeah, this same things as before. Probability of detecting object by camera is 80%. And probability of detecting correctly by LiDAR is 90%. LiDAR is more precise. And they are independent. And do that, oh, sorry, this is not with iClicker, but next example is for iClicker. So what is the probability of both sensors detected? Okay, you try it. So what is the probability of both sensors detect an obstacle? We know that probability of detecting by camera is 80% and detecting by LiDAR is 90%. What is the probability that both of them detect obstacles? Because they are independent, probability of C and L are multiplication of them. So just need to multiply. If you multiply 0.8 and 0.9 is A. Right? So for example, this is obviously wrong because it's more than 1. And if we multiply this is going to be P of C and L is equal to P of C multiply P of L, 0.8, 0.9, 72. Good. This example, I want you to do it. Use it, iClicker. Consider 2 events. Actually, this is a very good example. Different between mutually exclusive and independency. So can you open? I need to do that as well, I think. Go to iClicker. It's just to. Okay, I did. Oh, it's over there.
Ryan is giving this one.
No way, you checked it. You know when I'm all chilly. We be together, but and that isn't it.
Sorry, I can't. Okay, let's do it without that. Anyway, okay, I can ask you the question. I can't go there to bring that to select it, but how I can close it?
Not good.
It's not just me.
Yeah.
Good. Okay, so we want to see which one is the correct one. We have 2 events, A and B, and non-zero probability. That's kind of important part. Non-zero probability. Which of the following statement is correct? If A and B are mutually exclusive, then they are independent. If A and B are independent, then they are mutually exclusive. And a mutually exclusive event satisfy A and P of A and B is 0. That's correct. While independent events satisfy P of A and B is P of A multiply P of B. That's also correct. And the last one, mutually exclusive and independent event describe the same type of relationship. That is not correct. So which one is the best answer? Yes? C? Are you okay with C? What about A? Can we say, okay, if A and B are mutually exclusive, it means cannot happen at the same time, then they are independent. No, it's not always like that. That's correct. Also, we mentioned that A and B are non-zero. The probability of A and probability of B are not zero. That's another case. So the C is the correct answer. That's the difference between mutually exclusive events and independent events. We talked already about that. I think you got the point. Any question? OK. Another interesting rule that we just touched at before is complement rule. Complement rule can be explained by Venn diagram very nicely. In Venn diagram, if we have an event A, so because considering probability of all the universe is 1, because P of omega is always 1, so it means probability of all of this is 1. So it means probability of rest is 1 minus 1. So probability of this, that is A complement, probability of A complement is 1 minus probability of A. So this is called complement probability. That we already know that. It's simple. And it's coming from axiom 2. Remember, axiom 2 was a normalization. So normalization is important. The sum of all events complete, if they are complete, is 1. If they are complete means if they are covering all the universe. OK, so we're going to see another version of that soon. Let's clean up this. We have this example. And OK, example. Imagine we have an event. We are rolling a die. And event A is if the roll, if 6 coming. So probability of coming 6 is probability of A is 1 over 6, isn't it? Oh, it's not working. Okay. Freezed. Start. Okay, sorry, I need to restart PowerPoint. OK, so that was complement. OK. Good. OK, that was example. I mentioned that if probability of coming 6 is 1 over 6, probability of not coming 6 is 1 minus 1 over 6. OK, so probability of A is 1 over 6. What is probability of A complement? 1 minus 1 over 6 is 5 over 6. OK, so we have the clear version of that. Any question about the complement? It's simple. It's not that complicated. OK, but just general way of that is a total probability law. This total probability is very important. We can see that different version of that in like continuous space. Right now, we are still in discrete space. We have like A and B as events. And so the point of total probability is that computing a probability of an event like A by considering all different ways it could happen. If you know different ways that one event can happen, you can use this total probability. Imagine in Venn diagram also you can define it very nicely. Maybe I just use this. In this Venn diagram, all the probability divided by 3 ways, B1, B2, and B3. And A is one event that is in common with some of them, or for all of them. And we want to find probability of A. What is probability of A? So in this theorem, we mentioned that probability of A is actually sum of probability of A given all those events. Let B1, probability of B1, plus P of A given B2, probability of B2, plus P of A given B3, probability of B3. This is a total probability law. Why? We have that. We can prove this based off this diagram, Venn diagram. You can prove that because P of, let I write another with another color. P of A is kind of P of A and B1 plus B A and B2 plus B P A and B3. And this is also P of A and B1. Remember, chain rule? So this is proved already. So but maybe you ask me, this B1, B2, B3 are a little complex. What that means? By considering all different ways it could happen, I know it's complex. But in this example that I'm going to explain, next slide, everything is going to get clear. But proving this, any question about this proof? Because based off this Venn diagram, we put all these ants together and then wrote a multiplication rule, and we find that. OK, so let's see the clear version of that. So clear version is this. If you have n actually mutually exclusive events, mutually exclusive means when they add them together become 1. When we add B1, B2, B3, it's going to get 1. So we can write that. Okay, this is just general way of the things that I mentioned. Let's do this example. This example is going to clear everything. I took this picture actually yesterday I wanted to check it if I want to use bus to come to university. There is 2 ways to come to university. One, we call that route A, and the other one, imagine this is route A, and this dark blue is route B. So if you want to come to university, imagine there is 2 ways to come, route A and route B. OK? And you know that 40% of the students using, for example, route A, and 60% root B, okay? So these two are complete. So imagine this is all the space, and you have A and B. The set of students that using root A is in this part, and the rest are in this part. We have another information, and this information telling us students that using root A, there is 20% they get late. So getting late is another one. We call that late. And if a student using root B, 10% get late. So we know this information too. But what we want to find, P of being late. What is this? So this is complete everything that I mentioned. So you have different ways to get late using root A and using root B. And we just need to write the formula. So the probability of being late can be written as probability of getting late using A, probability of A, plus probability of getting late using B, probability of B. And if you add them together, we already have all this information. So we have 0.2, 0.4 plus 0.1, 0.6 equal to 0.08 plus 0.06 is 0.14. That's the overall. Okay, that's a good example to showing how we can use total theorem for this kind of examples. Oh, yes, that was the questions. Or what? Yeah, okay. What is the probability that randomly choose students and we get late? Okay, so we are good. Any question about that? Perfect. Last part of the class, we're going to talk a little bit about some other properties of probability. So also we have Venn diagram. In Venn diagram, we can see some of probability stuff, but not all of them. Okay, so in Venn diagram, you can see, for example, A and B. And also in this picture, you can kind of see the De Morgan law, because A complement and B complement is equal to A or B complement. This is De Morgan law, remember? And you can prove that this is why this is actually A complement and B complement using this De Morgan law. But we don't want to do that. We want to see some other properties of probability. The first one is probability of actually empty set is 0. It's normal, not very complicated. Probability of A complement is 1 minus probability of A. That we already talked about that, complement probability. But the new one is this one. If two events are not mutually exclusive, what's happening to probability of A or B? That's the formula. If A and B are mutually exclusive, this part is 0. It's the last property of axiom for probability, remember? But what about if they are actually mutually exclusive? If they are not necessarily mutually exclusive. It means if they can happen at the same time. If A and B are not 0, what's going to happen? We're going to see that in an example. But anybody can mention why we have this, how this is happening, why we need to remove this probability of A and B out. Let's check the Venn diagram. Maybe in Venn diagram we can get the answer before. OK. In this Venn diagram, this is A and B. OK. And P of A already covered A and B one time. And P of B is already covered A and B. When we are talking about probability, we are considering that volume. But if we write just P of A and B is equal to P of A plus P of B, we kind of 2 times add this A and B. So we need to take one of them out. So that's why we have this P, A, and B. Again, I explain. In P of A, we already have, because this is P of A. We already have P, A, and B. In P of B, also, we already have P of A and B. So we add them 2 times. So we need to remove one part out. That's why we get this formula. If there is not necessarily mutually exclusive, we need to eliminate this common part 1 time. Do you get that? OK. Let's do example. However, before that, before doing example, there is another property. That property called monotonicity or monotonic. Monotonic function in math, probably you had that before. We call a function monotonic if it is just increasing or just decreasing, and not like that. This function called monotonic. Increasing monotonic or monotonically increasing or monotonically decreasing. This is not monotonic because it's going up and down. A function that is always increasing or always decreasing called monotonic function. So mathematically, we can say, OK, if x1 is smaller than x2, f of x1 is also smaller than x2. So this is meaning of f of x2. This is a definition of monotony. But we have that also in probability. How? In probability, we mention if A is inside B, like we have like something like that. This is B, and A is inside that. A belongs to B. So probability of A is always smaller than probability of B. Makes sense. Look at that. Probability of A, for example, this is this volume. Probability of B is that. It's smaller. So this is called monotonicity probability. But all of these characteristics coming from actually axioms, probability axioms. You can see them. Or this Venn diagram. Okay, as I mentioned, they are coming from Kolmogorov axioms. Okay, last example for today is this one. We have a large class. Imagine your class. And event A is that a student passed the midterm. Probability of passing the midterm is, for example, 0.7. 70% pass the midterm. And passing the final is 60%. I'm sure it's not like that in this class, but imagine it is, okay? And probability, event A and B means students pass both exams. That is 0.5. Okay? We know those information. What is the question? Question is, what is the probability that randomly chosen students pass at least one exam? So at least one exam means P of A or B. Want to find this. Okay? If we just add P of A and P of B, this is not true because they are not mutually exclusive. And if you add them by mistake together, it's going to be even more than 1. Because 0.7 plus 0.6 is more than 1. It's not possible to have a probability more than 1. So we need to eliminate P of A and B. So this is going to be 0.7 plus 0.6 minus 0.5. And what's going to be the result? 0.8. Any question? OK, so next class, we're going to talk about Bayes formula. We are just ready for that. That Bayes formula is one of the important things that you're going to learn in this class, really. OK, have a good day. Next class, we're going to have quiz, the start of the class. It's just 15 minutes. It's not hard.
One asks for different.
I don't learn anything yet.